Alright, so we all probably know black holes are mysterious, right? A massive cosmic enigma, where gravity is so strong that nothing, not even light, can escape. But here's the thing. What if I told you that at the very heart of every black hole, there's something even weirder than we can imagine? That's singularity. Singularities. They challenge everything we think we know about the universe. These are places so extreme, so bizarre, that they push the very limits of our understanding. Imagine a place where gravity is so intense that it crushes matter into an infinitely small point, so small it has no volume. This is what we call a true singularity. As you fall closer and closer to it, space itself warps, and time begins to slow, almost grinding to a halt. Everything around you, everything you've ever known, space, time, even the very laws of physics, just collapse in on themselves. And that's not just theoretical, this is real, and it happens in the heart of every black hole. But here's the twist. Singularities aren't just confined to black holes. These mind-bending points of infinite density also mark the beginning of everything we know. The beginning of the universe itself. At the very core of the Big Bang, there was a singularity, a moment when all of reality as we know it was compressed into an infinitely tiny point before it exploded out to create everything we see today. Think about that for a moment. Every galaxy, every star, every planet, and even you, all started from a single infinitely dense point, a singularity. But what does that really mean? And why do these places mess with the very laws that govern the universe? How do we go from a singularity to the universe we know now? Alright, now let's talk about what happens when you actually get close to a singularity. Imagine yourself near a black hole, where the gravity is so intense that not even light can escape. You might think that time, like everything else, would flow just like normal. But that's where things get crazy. As you approach the black hole's event horizon, that critical boundary beyond which nothing can escape, not only does gravity start to stretch you, but time itself starts to slow down. Picture this. You're falling towards the black hole. To you, everything would feel normal, at least for a while. But if someone were watching you from a safe distance, they'd see you slowing down more and more as you approach the event horizon. Time for them is moving at its usual pace. But for you, it's like you're trapped in slow motion, like everything is happening in a frozen moment. The closer you get, the more dramatic the time dilation becomes. One of the most famous cases is the observation of stars orbiting the supermassive black hole in the center of the Milky Way, called Sagittarius A. These stars are located close to the black hole, within a region where time dilation should be noticeable. Astronomers have tracked the orbits of these stars using high-resolution infrared imaging, particularly using the Very Large Telescope, VLT, and other observatories. Some of the most prominent stars, such as S2, orbit very close to Sagittarius A*, completing an orbit in about 16 years. The extreme gravitational field near the black hole causes the orbits of these stars to behave in ways that are difficult to explain with Newtonian physics alone. The stars move faster and their orbits are more elliptical than predicted by classical mechanics. Time dilation, predicted by general relativity, also affects how these stars appear to an outside observer. The closer the stars are to the black hole, the more they experience time dilation, and the slower they seem to move when viewed from a distance. But it doesn't stop there. As you get even closer to the singularity, gravity becomes so strong that it starts stretching you. Imagine being pulled apart by an invisible force. This effect is called spaghettification. And no, it's not something straight out of a sci-fi movie. It's real. Here's what happens. Let's say you're falling into a black hole feet first. The gravity at your feet is much stronger than at your head, so your feet get pulled towards the black hole way faster than the rest of your body. As a result, you'd be stretched out in a long, thin shape, like a piece of spaghetti. Sounds wild, right? But that's exactly how powerful gravity near a black hole is. It stretches you in ways you could never imagine. This phenomenon isn't just a thought experiment, it's been confirmed both theoretically and through observations. For instance, we've observed time dilation with stars near black holes. The closer they get to the event horizon, the slower they appear to move from our perspective. And this effect isn't limited to stars. It's seen with light too. When light tries to escape the gravitational pull of a black hole, it gets stretched to the red end of the spectrum, known as gravitational redshift. This stretching of light confirms that time is running slower near the black hole. We've even captured real images that give us a glimpse of this strange environment. Remember the iconic Event Horizon Telescope image? That glowing ring of matter is a supermassive black hole in the center of galaxy M87. It's real data, not just a concept. And this image helps us see a world where the normal rules of space, time, and gravity no longer apply. It's like we found a window into a new reality, a reality where the laws of physics get bent and stretched to their breaking point. So how do singularities actually form? Well, it starts with stars. Imagine a massive star, at least 6 times heavier than our sun. These stars burn through their fuel over millions of years, just like a car using up gas. Once the fuel's gone, gravity takes over, and things start to get really intense. For smaller stars, like our sun, they'll just turn into white dwarfs or neutron stars, stable objects that don't collapse any further. But for really big stars, gravity becomes the ultimate force. Nothing can stop it. And the star collapses inward, becoming denser and denser until it forms a black hole with a singularity at the center. So, the singularity is the very core of a black hole, where all that mass has been crushed into an infinitely small point. As the star collapses, a critical boundary forms around the black hole, the event horizon. This is the point beyond which nothing can escape, not even light. Imagine you're inside this boundary. You can't see the singularity, but it's there, waiting, hidden from view. The event horizon acts like a shield, keeping the singularity out of sight. Now let's talk about 2 types of singularities: coordinate singularities and true singularities. Sounds complicated? Don't worry, here's the breakdown. A coordinate singularity happens when you pick a weird way of measuring space-time. It's like looking at the world through a funhouse mirror. It makes things look distorted, but if you change your perspective, it's totally fine. Take, for example, the Schwarzschild radius. This is the distance from the center of a black hole to the event horizon. When physicist Carl Schwarzschild first calculated it, he found 2 singularities, one at the Schwarzschild radius and one at the center. But guess what? The one at the Schwarzschild radius was just a coordinate singularity, a weird quirk in the math that disappears when you change how you look at it. However, the singularity at the center of a black hole is real. It's a true singularity, where density becomes infinite. Imagine squishing everything you've ever known into a point smaller than a grain of sand. It's so intense that even the best theories of physics can't explain what happens there. That's why scientists are still trying to figure it out. Alright, here's where things get really mind-bending. Remember how we said that singularities form at the heart of black holes? Well, the universe had its own singularity, right at the very beginning of time. According to the Big Bang Theory, about 13.8 billion years ago, the entire universe was packed into a single, infinitely dense point. Yes, everything we know today, planets, stars, even light itself, was once crammed into something smaller than a grain of sand. As the universe began to expand, space itself stretched out, giving birth to everything we see around us. Now, the Big Bang Theory does a great job explaining how the universe evolved after that point. But here's the catch. the moment of the Big Bang itself, the actual singularity at the beginning of time, breaks all the rules of physics we know. So let's talk about general relativity, Einstein's groundbreaking theory of gravity. It works perfectly well for large-scale things like planets, stars, and galaxies, but here's the problem. When we try to apply general relativity to the singularity itself, things go crazy. The equations just don't make sense anymore. They give us infinities, literally infinite density and infinite gravity. Imagine you're trying to measure something, and the answer keeps growing and growing without limit. This is what happens in the math at a singularity. When we ask questions like, what happened right before the Big Bang? Or, what does the space-time around a black hole's singularity really look like? General relativity just can't answer them. It reaches a point where the math breaks down, and we hit a wall of infinite values. This tells us that general relativity can't handle the extreme conditions inside a singularity. It's like trying to use a map of a city to navigate a completely unknown, uncharted territory. So, while general relativity is awesome for understanding the large-scale structure of the universe, it fails when we try to understand the very small, like the infinitely dense point of the Big Bang or the heart of a black hole. We need something more to explain these extremes. Here's where quantum mechanics comes in. Now, you've probably heard about quantum mechanics before. It's the theory that governs the tiny world of atoms and subatomic particles. It explains bizarre things like particles being in two places at once or the uncertainty of where something might be. But quantum mechanics works on very small scales, while general relativity works on the huge scales of planets and galaxies. The problem? They don't get along very well. General relativity is great for big stuff, but quantum mechanics rules the tiny world. But when we get to singularities, we need both. At a singularity, we're dealing with a situation where both incredibly strong gravity and tiny quantum effects are at play. Think about it, infinite density in a point smaller than a dot. General relativity tells us gravity is bending space-time, but quantum mechanics says particles behave in ways we can't predict. These two theories need to be unified to fully understand what's happening in such extreme conditions. That's why we need a theory of quantum gravity, a new framework that combines both. Quantum gravity would tell us how gravity behaves at the quantum level, where space-time itself is thought to be quantized, like a grid of tiny, indivisible units. This could prevent things from getting infinitely dense. If we had a theory of quantum gravity, we could explain what happens when space-time itself is squeezed into a singularity. We'd finally be able to answer the questions that have stumped physicists for decades. What happens at the Big Bang? What happens inside a black hole? And what exactly does a singularity look like? Now, quantum mechanics might hold the key. First, let's talk about string theory. Imagine for a moment that everything in the universe, the stars, planets, the air we breathe, even you and me, are made up of tiny little building blocks. But instead of those blocks being tiny particles like we might imagine, they're actually tiny vibrating strings, like little musical strings. Just like a guitar string can vibrate at different frequencies to create different musical notes, these fundamental strings vibrate at different frequencies to create different particles, like electrons or quarks. Each vibration of a string corresponds to a different particle in nature. For instance, one vibration might correspond to an electron, another to a photon, which is light, and so on. Now, why does this matter when talking about singularities and black holes? Well, in regular physics, particles like electrons or photons are treated as point-like, meaning they have no size. But in string theory, these particles are actually tiny one-dimensional strings, so the idea of something being infinitely small, like in a singularity, starts to make more sense. Rather than infinitely compressing into a point, these strings could prevent the complete collapse we see in a singularity, stopping the formation of that infinite density. String theory helps us think about singularities not as places where gravity crushes everything into nothingness, but as regions where space-time itself is woven together by these tiny vibrating strings. The math behind string theory could help us understand extreme conditions, like those near black holes or at the very beginning of the universe, without the infinities that break general relativity. Next, let's dive into loop quantum gravity, or LQG, another theory that's trying to fix the problem of singularities. To understand LQG, think of space-time like a fabric, kind of like the surface of a trampoline. In general relativity, we imagine this fabric being smooth and continuous. But loop quantum gravity suggests that space-time is actually quantized, like a Lego structure made up of tiny, indivisible blocks. In LQG, space-time isn't infinitely divisible. It's made up of the smallest possible chunks or loops. Think of these loops as tiny building blocks that make up the entire fabric of space-time. It's like pixels on a screen or grains of sand on a beach. These loops form a discrete structure, and no matter how small you zoom in, you'll always find these basic loops. They're the tiniest possible unit of space-time. So, when we talk about something like a black hole or a singularity, the idea in loop quantum gravity is that, at the very core of the black hole, space-time doesn't collapse to an infinite point. Instead, the fabric of space-time stops at the smallest loops, preventing it from crushing everything into infinity. This would mean that the concept of a singularity, an infinite collapse, doesn't happen. Instead, the loop structure of space-time keeps things from getting so dense that they become infinite. In simple terms, loop quantum gravity suggests that when you get to the center of a black hole, space-time's graininess kicks in. Instead of everything being crushed into an infinitely small point, the loops of space-time prevent it from collapsing further. This could mean there's no singularity at the center of a black hole at all, just a kind of quantum structure that stabilizes things. So how do these two theories, string theory and loop quantum gravity, help us understand singularities? They both try to remove the infinity that we see in general relativity. In string theory, the idea is that the smallest building blocks of reality are tiny strings that vibrate at different frequencies, and this prevents the formation of infinite density. In loop quantum gravity, the idea is that space-time is not a smooth fabric, but a granular one made of loops, which prevents space-time from collapsing into an infinite point. Both theories suggest that there's something new and tiny at the heart of singularities, something we've never been able to observe before. Whether it's the strings in string theory or the loops in loop quantum gravity, both could provide answers about the true nature of black holes and the beginning of the universe, places where general relativity just can't handle the math. These new frameworks could be the key to finally understanding what really happens when we encounter these mysterious points in space-time. In short, general relativity works beautifully for big things, and quantum mechanics explains the tiniest bits of reality, but they're two separate worlds. To understand singularities, we need to bring these two ideas together into one theory. This could unlock answers to the universe's biggest questions, like what happened before the Big Bang, or what's really inside a black hole. And while we don't have a final answer yet, the search for a unified theory of quantum gravity could be one of the greatest scientific breakthroughs of our time. But wait, there's more. Ever heard of naked singularities? These are some of the wildest concepts in modern physics. Imagine this. A singularity, that incredibly dense point at the heart of a black hole, exposed to the universe. Normally, we think of singularities as being hidden behind an event horizon, that boundary where not even light can escape. But what if there's a scenario where that boundary doesn't exist, where the singularity is out in the open, just sitting there, like a black hole without a cloak, exposing its mind-bending gravity to the rest of the universe. Now, if this were true, it would absolutely wreck our understanding of space-time. The laws of physics, as we know them, could break down in the presence of a naked singularity. It would be like discovering a loophole in the universe's rulebook, a crack in the fabric of space and time itself. But here's the thing. Scientists aren't sure if naked singularities actually exist. It's still a hot topic of debate. Some think they might be possible under the right conditions, while others argue that nature has some kind of built-in protection to prevent them from forming. In fact, there's a famous hypothesis called the cosmic censorship hypothesis, proposed by physicist Roger Penrose, which suggests that nature prevents naked singularities from existing in the real universe. But even this idea is being challenged by new theories and computer simulations. So who knows? Naked singularities might just be the next big mystery waiting to be solved. Now, let's dive into something even more mind-bending, the information paradox. Here's the situation. When matter falls into a black hole, it's gone, right? It crosses the event horizon, and that's the last we see of it. But wait, what about all the information that the matter carried? Information about what it was made of, where it came from, everything? Does that information just disappear into the void, lost forever? Or is it somehow preserved, even if we can't see it? Physicists have been arguing about this for decades, and it's one of the biggest puzzles in modern physics. If the information vanishes, it would violate one of the most sacred principles of quantum mechanics, the conservation of information. Quantum mechanics says that information can't be destroyed, it can only be transformed. But black holes seem to contradict this. If the information truly disappears, it's a fundamental break in our understanding of the universe. Some scientists believe that black holes might encode the information on their surfaces in a way we don't yet understand. This is called the holographic principle. Others suggest that black holes might actually evaporate over time, a process proposed by Stephen Hawking, and when they do, they could release the information in some new form, but we're still not sure how that works. Singularities are the ultimate puzzle of the universe, pushing the limits of our knowledge and challenging everything we think we know. Whether they're in the heart of black holes or at the beginning of time itself, they represent the frontiers of physics. As our technology improves, who knows what secrets we'll uncover next? The universe is full of mysteries just waiting to be solved. So stay curious and keep exploring. If you've enjoyed this deep dive into the mind-bending mysteries of singularities and black holes, don't forget to hit that like button. And if you want more mind-expanding content like this, make sure to subscribe to Noesis Corner. We've got plenty more science, space, and cosmic curiosity coming your way.